Hi class, this is Team Solo, and this is my final project presentation for Stats101B. According to the CDC, about 659,000 people die from heart disease each year in the United States. If we are able to predict the chances of an adult having heart disease, we could take precautions before it's too late, and it will actually save people's lives. To perform such a task, we'll be using an algorithm called random forest. The way we evaluate the performance of the algorithm is to look at its cross-validation score. The algorithm has 7 tuning parameters. Each of them has two levels, as you can see. Since each run is time-consuming, we want to find the best settings with as few runs as possible. Therefore, our task is to find the best settings of those parameters within 35 runs by designing an experiment. There are two strategies for designing the experiment. The first one is called fractional factorial design. In this design, it has a resolution of 4, and there's no alias between the main effects or between the main effects and the two-factor interactions. So the advantage of this design is that it evaluates all main effects without any influences. The drawback of this design is that there are 3 aliases of two-factor interactions, so this design could not examine all two-factor interactions. If the aliased interactions have a significant effect on our response, the performance of this design will be poor. In the optimal design, it requires 29 runs for all main effects and 2-factor interactions, but we add 3 more runs to give extra degree of freedom for estimating the error. In this design, all main effects and 2-factor interactions are partially aliased with each other, so we have to be careful with the multicollinearity. After we check the VIF score, there are no parameters with VIF greater than 2, so we don't have to worry about such an issue. Let's take a look at these two designs in their practical use. For the fractional factorial design, we have to carefully choose the generator so that the potentially significant effects are not aliased. Therefore, I would recommend the optimal design for this experiment. After choosing the optimal design, we are going to collect our response variable. Our initial model includes all the main effects and all the two-factor interactions. There's no straight line in the QQ plot, so the model violates the assumption of normality. To further improve our model, we have to select the significant parameters having p-value smaller than 0.05. I selected these 5 parameters for next model. This model has 3 outliers. After removing the 3 outliers, I obtained the final model. There is no violation of any assumptions. Here is the result. To further evaluate the final model, I conducted another 3 confirmation experiments, so there will be 35 runs in total. Absolute difference is less than 0.01, so this prediction is pretty accurate. In conclusion, both of my design and my model worked well. It is because the development of model follows statistical reasoning. It has accurate prediction with a R-squared score of 0.8573.